Yeah. So let's see here. All right. So today what we're going to do for our review class, right, our test is on Monday. We're going to go through the practice test. As you've noticed, right, there's a lot of questions in here. So, well, not a lot, but what I want to do is I want to start on the long answers, and then I'll post the solutions to the short answers. So whatever we don't get to, I'll just post the solutions for that so you can look back at it. So, yeah. So what you'll notice is that the assignment 3 is very similar to questions 10 and 11 on the practice test. All right, so we'll go through 10 and 11 today, and then you'll have kind of a good guide for doing the assignment. What's tricky about the assignment is the way the dates worked out is it's due on the test day, right? So definitely if you have questions about the assignment, then just ask me, and you can text or email or whatever, ask me questions about the assignment. But if you have a look at the practice test, they'll be very similar. Right? So test number 1 on Monday. Woohoo! Assignment number 3 is due on Monday. Questions 10 and 11 on the practice test are very similar. Right, so even though you don't have the solutions, the volume up on this? Or am I just hearing things? I don't actually know if that helped or, yeah, okay. It's just me hearing things. Okay, so they're very similar, but again, just, oops. Ask me if you have any questions about the assignments. Any questions about the assignment? So they kind of go hand in hand. They're both practice for the test. So on the practice test, number 1, let's say solutions. I'm just going to go steal the little printouts here. One thing that I should note here, when I said make a tree diagram, I actually meant stem and leaf plot. So that's question 7 on the practice. That'll throw you for a loop. But it also should make more sense when you're trying to do it. Like I said, I got my trees and my leaves mixed up. Happens. So what I've done is it's going to be kind of 2 parts, multiple choice and then long answers. Right? So I'm telling you everything that I'm expecting you to know for each multiple choice section. So question 1 will be 10 multiple choice, just from all these things, right? Chapter 1 stuff. So if I give you a summary of a data set, right, I'll ask you to identify, and I'll give you the descriptions of the variables as well. From there, you should be able to identify if a variable is categorical or numerical. And if I give you a research question, identify which is the response variable and which ones are the explanatory variables. Then I have this very vague data collection point. Really, the take-home message here is make sure that all your data is randomly selected. That was kind of the only thing we really landed on in class. For the visualization point, it goes back to, okay, well, what kind of variable was this variable, right? If it's categorical, you would visualize it with a bar graph. And if it's numerical, you would visualize it with a histogram, right? So it's kind of a two-step question. And then describing the center and spread of distribution. So if you have a normal distribution, then you're going to use the mean and the standard deviation. And if it's clearly skewed, you should be using the median and the interquartile range, right? So just applying that. Calculate the standard deviation. How rude. I'll do it for 4 or 5 points, probably 4 points, right? So 4 or 5 points. So just know how to calculate the standard deviation. Right? And there's practice in the practice test. Again, if I give you a set of numbers, you have to find the 5-number summary, and then in a multiple choice question, you would just pick the right option. And then use the 1.5 IQR rule to identify if there's any outliers or not. I can't remember what I did, but this could be done just using the 5-number summary, right? Because if you find your bounds and the minimum and the maximum are within those bounds, then there are no outliers, right? So you can just look at the max and the min to see if those bounds are inside or outside your data. So could be done using just the 5-number summary. And then, given a 5-number summary, pick the box plot that represents that 5-number summary. Remember, a box plot has the median in the center, and then to finish off the box, you've got Q1 and Q3, and then it goes to whatever data points are within the upper and lower bound, and then indicating outliers by stars. So just pick the right box plot. And then make a stem and leaf plot, not a tree diagram. I guess this is crossed out too. Any questions about that? So just kind of testing our way through chapter 1. Chapter 2, multiple choice. Oops. Okay. So then there's 15 multiple choice questions from chapter 2, part of which is just going to be testing theory, right? So what does it mean for two things to be disjoint? It means that they can never happen at the same time, for example, right? What is the sample space? The sample space is a list of all possible outcomes. If I give you a probability distribution, so remember in class I had 3 and we had to pick the valid probability distribution. So then you had to check 3 things. 1, that all the outcomes were disjoint. 2, you check that all the probabilities are between 0 and 1. If you find one option that doesn't have a probability that's between 0 and 1, or that has a probability that isn't between 0 and 1, say that instead, it's out, right? It can't be a valid probability distribution. And then the last thing that you check is that the total probability has to be 1, right? So if the sum isn't 1, then it's not a valid probability distribution. Okay. The general addition rule is just going to be a question where you apply the general addition rule, which is on your formula sheet, the probability of A or B is the probability of A plus the probability of B minus the probability of A or B, or sorry, and B. Makes a difference. So a question where you apply that formula. I'll skip down to the complement of an event because that's where we'll get the formula for the general multiplication rule. But the complement of an event is where you use the formula, the probability of A given B is the probability of A and B over the probability of B. The general multiplication rule is this formula just readjusted so that you're solving for the probability of A and B. So you just move the probability of B over here. So the general multiplication rule is the probability of A and B is the probability of A given B times the probability of B. Oops, that wasn't the complement. I'm out to lunch. Conditional. Sorry. The complement of an event, the probability of not A is 1 minus the probability of A. In terms of formulas. And then we've checked for independence on assignment 2, right? And so that's when we just say that if A and B are independent, then the probability of A and B has to be the same as the probability of A times the probability of B. Right, so you can check that. If they're not the same, then they're not independent. And then just in general, find probabilities using a contingency table or a probability table. So that's like question 8 on the practice. Any questions about that one? So, like I said, I want to go through the long answer questions, and then whatever we have time for in the multiple choice we'll go through, but otherwise I'll just post the solutions after class. So after that, right, you had 3 long answer questions. The first one is going to be an actual tree diagram, a real one, and then the normal distribution, and then the binomial, which we just covered last day. Oh, I guess I gave you a little thing to think about, the normal approximation. I guess I can't really sneak it in here. I forgot. But I'll show you how to do it on here. And then once you find your Z-score, it's just back to a Z-score. All right, we'll do this one, and then I'll cover the last little bit from last day with the binomial that we're about to do. And start on 9. I made these probabilities up, so don't bet any money on it. But the probability of a clear day at Big White is 0.55. So assume that if the weather is clear the previous day, the probability of a clear day is 0.7. If the weather was not clear the previous day, the probability of a clear day is 0.35. You're going skiing for 2 days. Sounds familiar, right? You went on a sightseeing boat tour on 2 consecutive days, right? So we've got day 1, day 2. And so we can start doing A. Build a tree diagram labeling all the appropriate probabilities, including the probabilities at the end of each branch. Got it. First, what I'm going to do is I'm going to let C be a clear day. So first, I'm going to go out here, give myself lots of room. Day 1, it was either clear or not clear. And we're told that the probability is 0.55 of a clear day. And so the probability that it's not clear on the first day is 1 minus that, so 0.45. And then these branches kind of change depending on if it was clear on the first day, clear on the second day, or not clear on the first day. So I'll draw my branches here. Day 2, it's a new day. So it can be either clear or not clear, clear or not clear. Doesn't matter what happened on the previous day. Here's where we're told, okay, so assume that if the weather was clear the previous day, the probability of a clear day is 0.7. So on the left-hand branch, we've got a clear day, so then the probability of a clear day here is 0.7. Okay. So then the probability of a not clear day is 1 minus that 0.3. Okay. If the weather is not clear the previous day, the probability of a clear day is 0.35. So not clear is the second branch, and so the probability of a clear day is 0.35. And then the probability that it's not clear on the second day, again, then would be 1 minus 0.35, 0.65. So here, I like to just jot down all my combinations at the bottom, right? So on the first branch, we had a clear day, then a clear day, or we had a clear day and a not clear day, a not clear day and a clear day, and then a not clear day, not clear day. To find the probabilities of each of these combinations, we multiply down each branch, right? So the probability of a clear day and a clear day is 0.55 times 0.70. 0.55 times 0.7, 0.385. Just give myself a little bit more room here. So the probability of a clear day and then a not clear day is 0.55 times 0.30. 0.165. Moving on, the probability of a not clear day and then a clear day is 0.45 times 0.35. 0.45 times 0.35 is 0.1575. And you don't want to round these numbers because they have to add to 1 later, right? And then finally, the probability of a not clear day is 0.45 times 0.65. Clean that up a bit. .45 times 0.65 is 0.2925. as a check, just to make sure that you've done this, all these probabilities right, these branches, they all have to add to 1, right? So as a quick check, you can just make sure that they total to 1, and that's why you don't want to be rounding any values here. So just do a total is 0.2925 plus 0.1575 plus 0.165 plus 0.385. 1. Woohoo! Oh, my eyes got close together. Oh, so they total 1. How I'm going to distribute these marks on here is this is going to be 4 marks, 1 mark, 1 mark, and 2 marks. And C was a little bit sneaky. I'll show you what I meant to say, but what I didn't really say. But we'll do B first. Any questions about A before we keep going? Yeah. So that's a lot of work, right? But now we can use these probabilities just to answer the questions. So part B was asking for what's the probability that you have a clear day on both days? So the probability of a clear day and a clear day, just from up above here, the only way that that can happen, right, is to go down the clear day branch and then another clear day branch, so 0.385. You've already shown that calculation, so you don't have to show it again. You can just say the probability of a clear day and a clear day is 0.385. So C, here's where things got rough. What's the probability that you don't get a clear day on either of the days? I kind of messed that up. What I meant to say was that it's not clear on both of the days. Makes more sense. That it's not clear, ironically, on both of the days. On both days. That's a little bit better. Well, not clear on both of the days. The only way that can happen is the not clear and the not clear, which we know the probability is 0.2925 because we already found it. So the probability of not clear is 0.2925. And I'll make sure that the questions on the test are a little bit easier to read than that one. That one is sneaky. Part D, what's the probability of at least one clear day? So the probability of at least one clear day. We have 2 ways of solving this, right? We could say, okay, well, here we have 2 clear days, so that one satisfies the criteria of at least one clear day. Here we have a clear day, one not clear day, still good. Not clear, but then a clear day, so still good, right? At least one clear day. So all these 3 satisfy the criteria. So what we could do, we could add up these probabilities and get that total probability. Or we can say, well, because they add to 1, we can just take away the one that doesn't satisfy that criteria, or use the complement. Doesn't matter how you do it, you're going to get to the same number. So as long as you show me what you're doing, either way is fine. So I'm going to put both on here. It's the probability of a clear day, plus a probability of a clear day, not clear day, plus the probability of a not clear day, which is the same as 1 minus the probability of a not clear day, which is the one I'll use, 1 minus 0.2925. Let's see. I get 0.7075, but I did it kind of quickly. either way, if you added up those three probabilities, you would still get 0.7075. So it's a probability of at least one clear day. Any questions about that one? Okay. So then let's move on. Manatees. So here we've got a normal distribution question. And normal distribution questions always start the same way. So blah, blah, blah follows a normal distribution with a mean this and a standard deviation this. Find probabilities, or if I give you the area under the curve, use it to find the cutoff values. All right. So manatees travel at a speed that's approximately normally distributed with a mean of 3.8 miles per hour and a standard deviation of 1.34 miles per hour. Great. Part A, what proportion of manatees travel faster than 4.7 miles per hour? Okay. So what you're gonna do is we're gonna draw out this normal distribution. It always starts the same way, right? Because we're told it follows a normal distribution and the mean is 3.8. So you can always just draw the center line is 3.8. So that's not going to move around. And then just jot down that sigma is 1.34 somewhere. Okay. Remembering that this is, so the bottom line here is just the number line. So when we put 4.7, which is the speed that we're interested in this case, it just goes somewhere above here. So 4.7. It doesn't matter where you draw it, you're just trying to visualize what area you want. And so we want to know what proportion of manatees travel faster than 4.7 miles per hour. Proportions, probabilities, and percentages, those are all areas under the curve, right? Those three P's all mean the same thing, the area under the curve. So to get this area under the curve, right, we have to convert our x, our 4.7, to a z-score, and then we can use the z-table to find this area. Okay. So we'll start with z is x minus mu over sigma. X is always going to be the value that you're interested in, right? So the 4.7 in this case. So 4.7 minus 3.8 divided by sigma, which is 1.34. So I get 0.9 over 1.34. I'll do all my decimal places, and then we always have to round z to 2 decimal places just because that's all the table can handle. And so we get 0.671641791. So approximately 0.67. Z must have 2 decimal places. So now we can use our Z table. There. We have a positive Z, so we have to go to the positive Z side. And we had 0.67. So our whole number is 0. And then first decimal place is 6. So then we have to join it up with the second decimal, which is 7. And so 0.7486. That's the area to the left of a Z of 0.67. We want the area to the right, but what I'm going to do is I'm going to write out the area that I found in case things go wrong halfway through. So remember, you have 2 options for communicating what you just did, right? You can write it out in words, or you can use probability notation. So I'm going to show you both, and it'll be your choice. So you can write out this blurb using the Z table. We find the area to the left of Z equal to 0.67 is 0.7486, was that right? Let me just check because I don't remember. 0.7486. Hey, that's what I had. Not bad. So that's this area. That's okay. We know the total area is 1, right? So then we know that this area must be 1 minus 0.7486. So therefore, the area to the right is 1 minus 0.7486, which is 0.2514. When I'm marking these, all I'll be looking for is the number. I don't actually read what you write. So if you don't want to write a blurb, it's okay. But it's nice to write a blurb. Get in the habit of writing a blurb, right? Just to answer the question. So that's what I'll do. What was the question? I just reword the question as an answer. The proportion of manatees that travel faster than 4.7 miles per hour is 0.2514. Therefore, oops, what the proportion of manatees that travel faster than 4.7 miles per hour is 0.2514. So what I'm going to do is I'm just going to show you the probability notation that you could use to replace using the Z table blurb. You could say that the probability of Z being greater than or equal to 0.67 is 1 minus 0.7486, which is 0.2514. If you wanted to write that instead, then that's correct as well. A little shorter, but a little harder. So choose your battles. Oh. Any questions about that one? Okay. How about part B then? What is the probability? Remember, probability is just the area under the curve. So what's the probability of a manatee that travels slower than 1 mile per hour? Same sort of question, right? Just kind of getting you into it here. .8. Sigma is still 1.34. So this empty shell will be the same for all the questions. But now we're down here at 1 mile per hour, and we want to know what's this area here. So same deal. Find your Z score. Z is x minus mu over sigma. X in this case is 1 minus 3.8 over 1.34. Divided by, so negative 2.8 divided by 1.34. I get negative 2.089552239. Again, we have to round to 2 decimal places. If you jump to just rounding to 2 decimal places, that's fine. I just want to show you what it is. Negative, roughly equal to negative 2.09 to 2 decimal places. Okay. Now again, we'll go to the Z table. Now we're on the negative side, right? And so negative side for Z, our whole number is negative 2 and then 0.09, so negative 2.0, and then 9's way over here. We can let's go over here. 0.0183 is the area to the left. Unless my eyes skipped around, but it sounds kind of familiar. So again, using the Z table, we find the area to the left of Z equal to negative 2.09 is 0.0183. Is that it? Yeah? Cool. And that is the area that we want, right? Just judging by our little graph that we made, right? We want the area to the left, so we can leave it there. So to answer the question, the probability of a manatee that travels slower than 1 mile per hour is 0.0183. Therefore, the probability of a manatee that travels at speeds slower than 1 mile per hour is 0.0183. Just show you the probability notation, right? Optional. The probability that Z is less than or equal to negative 2.09 is 0.0183. Any questions about that one? Okay. All right. Oh, what am I doing? I wanted to just scroll up here. C. How slow do the slowest 15% of West Indian manatees travel? So now I went species specific. Doesn't matter. Should have just said manatees. So how slow do the slowest 15%? So now I'm giving you an area under the curve, and you have to find the cutoff value, right? So working backwards to find X. So C, again, you're going to draw out your normal distribution centered on 3.8, and sigma is still 1.34. And now we want the slowest 15%, which is 0.15. You'll always want to convert your percentages just to decimals for the areas under the curve, just because the table entries in the table are decimals. So now we're forcing this area to be 0.15, and we have to find out what this value is. So this is where we said last day we have this kind of pendulum situation. So X we have to convert to a Z, and then we have to use the Z table to find the probability. But we can work the other way as well, right? I've given you a probability, which you have to turn into a Z, and then you can solve for X. Same idea. So X goes to Z by Z is X minus mu over sigma. And Z goes to a probability using the Z table. now we just use the Z table to convert the probability to a Z score, and then use that Z to solve for X. So what we're going to do is we're going to go to the table. We know 0.15 has to be on the negative Z side, right? Because it's below the mean. Right? At the mean, you have an area of 0.5 to the left and 0.5 to the right. So 0.15 has to be on the negative side. So what you're going to do is you're just going to cruise the table to figure out which one of these is closest to 0.15. And so jump around here, and it'll be between these two values, right? 0.1515 and 0.1492. And so I just use my calculator to see which one is closest. And so 0.15 minus 0.1492 is 0.0008. I call it 8 away. In my mind, it's 8 away. Whereas just looking at 0.1515 is 15 away. That makes sense? From 0.15. And so this one's a closer one. Like I said last day, if you end up picking the wrong one, as long as you tell me which one you're going to use, or which one you think is the closest, I'll just count it as a typo, so half mark off. And then as long as you follow through correctly, then you're safe. Okay. So, but this one is technically the closest. And so we're going to map it back to the Z score that it corresponds to. Where did it go here? So this corresponds to a Z of negative 1.04. I'm going to write that all down. Because that's how that's the only way that we can show our work for this type of stuff, right? Writing it down. So using the Z table, we find the table entry. Remember the table entry, just flipping back to the table here for a sec. These are the table entries, right? And it says that here, the table entry is the area under the curve. And so these are all table entries. So you can refer to them as table entries. Using the Z table, we find the table entry closest to 0.15 is 0.1492. So far, so good. Which corresponds to Z equal to, and now I can't remember, negative 1.04. Let me just check. Where were we here? Negative 1.04. Here. Good. So now we have our Z score. And so we can say, well, Z is X minus mu over sigma. Now I know Z is negative 1.04, and I'm trying to solve for X. Mu is still 3.8, and sigma is still 1.34. Or if you're having a peek at your formula sheet, you could also use X is mu plus Z times sigma. I think that's the order I have it on. Yeah. Which is just that same equation, rearranged, solved for X. So whichever way you prefer. So now solving for X, I like just working with one formula and rearranging it to what I need. So I'm just going to use the original. 1.04 negative times 1.34 is negative 1.3936, which is X minus 3.8. Add 3.8 to both sides, and I get X is 2.4064. I'm not going to round this. I'm just going to keep it. So whenever you can, just keep as many decimal places as you can. Or as long as you've shown me your work, you can round it later, right? If it's important, I'll tell you, give the answer to 3 decimal places or give the answer to 2 decimal places. Otherwise, it's kind of your call. Okay? We're not doing anything with sig figs because that means I have to teach you sig figs, and I don't want to. Doesn't matter. I don't care about them. I care about them. I just. So, just kind of keep as many decimal places as you can. So therefore, the slowest 15% of manatees travel, oops, what the? Travel at speeds up to 2.4064 miles per hour. Because if you look at your graph, right, here's the slowest 15% up to 2.40 whatever we found, right? And so the slowest 15% they travel at speeds up to this point, but also they could be slower than that. Any questions about that one? Oh, okay. Oh, no. D. What speeds capture the central 90% of Manatee speeds? So now we want the central 90%. Okay. This is going to be similar to the one we just did, just 2 parts. So part D starts the same way, right? Normal distribution centered on 3.8, sigma is still 1.34. And now we want the central 90%. So somewhere between here and here, we're going to force this area to be 0.90. And this is going to be some x lower and some x upper. We did something like this, but in the reverse, right, where we had to find the area between 2 values, finding the 2 values that capture the central 90%, for example, or the central whatever. It's actually a little bit easier, so that's why I have it on here. I'll show you how to do it. So we know, right, we know that the central 90% has to be in here. So it's symmetric, we know that. So then 0.9 here, 0.1 left over, split evenly amongst the 2 tails. So we've got 0.05 here and 0.05 here. So we can do 0.05 here and 0.05 here. Total area has to be 1. So what we can do, just like we did before, right now we can force this area to be 0.05 instead of 0.15, right? But same idea. So we can force this area to be 0.05, and then this area, same idea, right, would have to be 0.95. Right? So not just the 0.9, but also the rest of that tail there. 0.95. Or a sneaky way we could do, and which I encourage you to do, is to recognize that, okay, well, Z is symmetric around 0. Right? So if we've got the central 90%, then this Z is going to be some value, the negative version of that value, and this Z will just be the positive version of the same value, right? Because the area in the tails has to be the same. So I'll show you what I mean. All right. First, I'll say find XL. So using the Z table, we find the table entry, right? That's what we're going to go for. The table entry closest to 0.05 is, and if memory serves me, there's actually two values that are same distance apart, so you can just pick one. But let's just have a look here. Cruising the table here, we've got 0.0505 and 0.0495. Those two values are the ones that are closest to 0.05. Both of them are 5 away. And so it actually doesn't matter which one you choose, as long as you tell me which one you're going to choose. Fine. And so I'll write that down. Is either 0.0505 or 0.0495. Like I said, I'm just going to say which one I'm going to choose. I will choose, or I will use 0.0505. How about? Doesn't matter. Which corresponds to Z equal to, now I have to go back here, focusing on 0.0505, 0.0505 here has a Z of negative 1.64, or if you wanted to use 0.0495, negative 1.65. Doesn't matter. Slightly different answers, but like I said, as long as you tell me which one you're going to use, that's fine. Which corresponds to Z of negative 1.64. So Z is X minus X lower minus mu over sigma. Negative 1.64 is X lower minus 3.8 divided by 1.34. So I've got 1.64 negative times 1.34 plus 3.8. I get an X lower of 1.6024. Hopefully I clicked that right. Looks okay. So that's the lower bound. Now we have to find the upper bound. So now find X upper. Here's where you're going to find, you could either go ahead and find 0.95 in the table entries, find the value closest to it, but what you'll notice is that it's going to be 1.64 or 1.65 depending on which you choose. Okay? So by symmetry, I know Z is 1.64 on the upper bound. So then I know Z is X upper minus mu over sigma. So 1.64 is X upper minus 3.8 divided by 1.34. 1.64 times 1.34 plus 3.8. I get an X upper of 5.9976. Therefore, the central 90% of speeds are between, what did we say here? 1.6024 miles per hour and 5.9976 miles per hour. If you wanted to round those to maybe 2 decimal places, that's fine. No less than 2. Try to stick to 2 or more. Any questions about that one? All right. So let's see here. Here's a binomial question. Manuel is a processor tester at Intel. Sounds important. He knows that the probability of a processor being defective is 0.03. For quality control, he randomly tests 10 processors from every box. Fair enough. What is the probability that 2 processors in the box are defective? So you could go ahead and make a tree diagram, but it would have to have 10 layers, right? 1 for each processor. It's either defective or not defective, defective, not defective, defective, not defective. That sounds like a lot of work, right? And so we move over to the binomial distribution, which is our way of handling those kind of big tree diagrams. And so part A, what's the probability that 2 processors in the box are defective? So we're going to use that binomial formula that we developed last day. So we say the probability that x equals k, just in general, the formula is n choose k, right? Not a fraction, but n choose k times p to the k times 1 minus p to the n minus k. In our case, right, k is the number of successes, n is the number of trials, and so in this case we're interested in k equal to 2, and we have 10 processors that we're going to check, so that's 10 trials. And the probability of a defective processor is 0.03. So we've got n is 10, k is 2 in this question, and p is 0.03. So now we can do our formula here. The probability that x is exactly 2, bless you, defective processors is 10 choose 2 times 0.03 to the power of 2 times 1 minus 0.03 to the power of 10 minus 2. 10 choose 2 on your calculator, right, is just 10 on the screen, and then, well, second plus for if you're working on this calculator, right? So second, it's the NCR button or NCK button. And then it won't look like it's doing anything, but it's waiting for the 2, and then equals, and I get 45 is that value. Okay. So just make sure that that's what you get when you do 10 choose 2 on your calculator. And then I'll just leave 0.03 to the power of 2 here because I'm going to simplify this other portion. 1 minus 0.03 is 0.97 to the power of 10 minus 2, which is 8. Just kind of showing my work as I go here. So then I get 0.03 to the power of 2. I have 45 times 0.0009 times 0.97 to the power of 8 is 0.78374335. Now I can just multiply these out times 0.0009 times 45. The probability of 2 processors exactly out of 10 being defective is 0.0317411606. And I would just leave it with all those decimal places, even though it feels tedious, okay? Because we don't know how small these differences are going to be, right? So we're going to keep all these decimal places just in general. For binomials, keep all your decimal places. Any questions about that one? No? Part B. What's the probability that there's more than 2 defective processors? So the probability of more than 2 defective. Oops, not a question mark. 2 ways we could do it, right? We have two defective, or 3, or 4, or 5, or 6, or 7, or 8, or 9, or 10. Sounds like a lot of work, right? Or just remembering that the total probability has to be 1. So what you can do is you can just find the probability of 0 defective and the probability of 1 defective, subtract those from 1. Much easier, right? Then you only have to find 2 of them instead of, oh, whatever, a lot of them. So I'm just gonna encourage you to just do that. Of course, you would get the same answer if you did all of them, but it would take you all day. 1 minus the probability of 0 minus the probability of 1. Just taking away 0 and 1 defective ones will leave you with 2 or more. So I'm going to solve these individually, and then I'm going to plug them back in. So the probability that x is 0 is 10 choose 0 times 0.03 to the power of 0 times 0.97 to the power of 10. 10 choose 0. It's just going to be 1 times 1 times 0.97. Oops. I'll just do it. 0.97 to the power of 10 is 0.7374242127. I'm going to store that in my calculator, right? If you remember how to store stuff. If you don't, just ask me after class. I'm going to store it in 1. So that makes 0.7374242127. Just make a note to myself that I stored it in 1. Same thing, the probability that x is 1 is 10 choose 1 times 0.03 to the power of 1 times 0.97 to the power of, I'm just going to go right to 10 minus 1 is 9. Only because I know I'm cutting it close and I want to get to that last one. 10 choose 1. Oh, what the? It's 10. Phew. Got to my days between dates functions. You guys all remember those? .97 to the power of 9 is 0.7602311059 times 0.03 times 10. This is 0.228069318. Just for kicks, I'll store this in 2. So now the probability of more than 2 defective is 1 minus the probability of 0 minus the probability of 1, which I'll make a little bit more room for myself here. 1 minus 0.737424127 minus 0.228069318. I get 0.034506556. Hopefully I did that okay. Looks about right. Yeah.
So it's more than 2. Should we also subtract the probability of 2?
But I'm making it inclusive because I got lazy.
So if it's more than 2, we would take out the 2 as well, though?
Yeah. Yeah. And on the test, if you're not sure which I mean, then just ask me. Okay. All right. Any questions about that one before we go to C? This is the part where I kind of left you to your own devices last day. And you know what, just to simplify things, because it's a long ways up. C, suppose Manuel's coworker, because Manuel can't handle it, Ricardo, tests 500 processors. So now we're working with 500. You use the normal approximation, make sure to test the conditions to find the probability that he will find 20 or less defective processors. Okay. So on your formula sheet, you know the mean and the standard deviation of a binomial. Okay. So first, mu is n times p, and now our n is 500, right? The number of trials times p, which is 0.03. So 500 times 0.03, 15. So out of these 500, we're expecting to see about 15 defective processors. Okay. Sigma is the square root of NPQ. Remember where Q is just 1 minus P, so we get the square root of 500 times 0.03 times 0.97 is the square root of 14.55, which is 3.81444625. Okay. So now we know the mean and the standard deviation. And so we have to test the conditions, which I kind of left you to read on your own. But what we have to make sure is that our sample size that we're working with is large enough so that n times p has to be greater than or equal to 10. So in this case, n times p is 500 times 0.03. which is 15, which is greater than or equal to 10. You have to expect to see at least 10 defective processors in order to use the normal distribution, but also n times q has to be greater than or equal to 10. So 500 times 0.97, 500 times 0.97 is going to be 500 minus 15, but 485, which is, of course, greater than or equal to 10. So that's how you check those conditions. So now, use the normal approximation to find the probability he will find 20 or less defective processors. So now, because these conditions check out, we can use a normal approximation to say, well, it's centered on 15, and sigma is 3.814, let's say. And so now we want to know, well, 20 is the value we're interested in, 20 or less defective processors. So now we're back to this normal distribution problem. right? Where Z is X minus mu over sigma. And so we have Z is 20 minus 15 over sigma, which we found was 3.814. So 20 minus 15 divided by 3.814, I get a Z of 1.310959622. So Z is approximately just the 2 decimal places, right? 1.31. Now, using the Z table, 1.31 is on the positive side. 1.31, the probability of 20 or less is 0.9049. I'll cheat and say the probability that Z is less than or equal to 1.31 is, what was it? 0.9. Thank you. Good. So I'll post the rest of those solutions, but you are good to go. All right. See you on Monday.